Hey there, Year 9s, Mr. Herman here, and this is a new topic, Chapter 7, Parabolas. And this exercise here, 7a, will be exploring parabolas, and specifically the properties of parabolas. The learning goals for this lesson is to know the shape and symmetry of a basic parabola y is equal to x squared. And the success criteria for this lesson is to be able to identify the key features of a parabola from a graph, and to also be able to observe the impact of transformations of the graph y equals x squared. Now, just like new topics, the starting of looking into parabolas is quite simple. One of the simplest and most important, non-linear being a key word, graph is a parabola. So when a ball is thrown or water streams up from a garden hose, the path that it creates, it follows what's called a parabolic shape. Now, to dissect para, the prefix have many definitions, but para itself, the main definition for it just means beside. So when you draw the shape of a parabola, there's a mirror image that happens. Now, there's much debate about the word bola and why it's called bola, or why it's being used, and it dates back to the Greeks using the words. I'm not going to delve in that too much. For now, the parabola is a graph of what is a quadratic relation with the basic rule of y is equal to x squared. So y equals x and y equals x squared goes into completely different territories. When we looked into y equals x plus 3, y equals 2x or minus 3x, it followed a linear format, and it had transformations, but effectively the line goes left to right, up and down, or left to right, down and up, and we look into the different properties like the gradient, the steepness, the transformations of y-intercept and x-intercept. Y equals x squared, and you can have different properties of an x squared. You can have something like y equals x squared plus x, or y equals minus 3x squared. As long as one of the terms has the highest power of 2, we are dealing with quadratics, and when sketched, or graphed into a Cartesian plane, we're dealing with parabolas. As soon as you venture into y equals x to the power 3 or any other type of number with a higher degree power, we're straying away from quadratics. This gets into cubic functions, which is something completely different. But for this here, and also these different types here, quadratic rules such as x minus 1 all squared, or 2x squared minus x minus 3, every single one of these has a highest power squared, or 2. And because of that, we'll be dealing with quadratics. And we look into the different properties of when sketching these different types of quadratics. Well, what I'm going to show you now is the basic forms that you can get of a normal quadratic graph, and this stems from the basic one: y is equal to x squared. And there's different types of y values that we can take on. I'm going to look at these 4 different types here. So what happens is, when you sketch the graph of y is equal to x squared, just like any type of graph, you're going to come up with different x values to put into the formula, and it's going to spit out its corresponding y value. So for instance here, when y is equal to negative 3, so y is x squared, when y is equal to negative 3, this is negative 3 squared. A squared number, or a negative number squared, results in a positive number. So negative 3 squared will result in 9, and this is what we have here. In fact, any negative number that you square will result in a positive number. So here we have negative 1 squared, which is just 1 times 1. This will give me positive 1. 0 squared is obviously 0, and then 1, 4, and 9. So when we sketch this, we have got these 7 different points. We'll start with here, this is 0. When x is equal to 1, y is equal to 1, so we have a point here. When x is equal to 2, y is equal to 4, we have a point here. x is equal to 3, y is equal to 9. So you can see here that there's this growth, but there's this exponential growth. For every one we go across, and it bumps up quite a bit. In fact, when you get to 4, it will end up at 16, which is really far up the vertical part of the axis. When you sketch this, you actually don't connect it line. It actually makes what's called a parabolic curve. That was a terrible one. Let's try again. There we go. I've also mirrored this on the left-hand side of the y-axis, and remember that for every negative value, we'll also have this positive corresponding y value. And this is why we have this mirror image here. The graph itself doesn't necessarily tailor down towards the negative quadrant where both x and y values are negative. It actually stays within the positive part of y, and that's because when you square a negative number, it turns positive, and this is where that mirror image is. So this is your basic graph of y is equal to x squared. Just remember that it does curve right around. My curves are a bit sketchy. Now for y2, which is equal to negative x squared, this is the same process. When we have y is equal to negative x squared, this is implying we have y is equal to negative of negative 3 squared, which is the first one, and we know that negative 3 squared will give me a positive 9, but we have this negative hanging out in the front, so it ends up being negative 9. So we've taken this, squared it to get positive 9, and that negative implies that it becomes a negative. So when x is equal to negative 3, we have negative 9. When x is equal to negative 2, we have negative 4, negative 1, 0. Then when we get to the positives, we have y is equal to negative 1 squared. 1 squared is just 1, and because of that negative in the front, this becomes negative 1. So in fact, we have this kind of inverse properties happening with these numbers here. And so when we sketch it, like this, we end up getting this inverse version of the y equals x squared. In fact, it's mirrored at the x-axis. And this here is negative x all squared. So there are these interesting properties which is vastly different to the normal y is equal to x linear graphs. We venture into different properties. When we look at y3 is equal to x minus 2 all squared, when we try to substitute negative 3 and negative 2 into here, so y3 is equal to x minus 2 all squared. So let's substitute negative 3 into this. This will be negative 3 minus 2 all squared, which is equal to minus 5 all squared. When you substitute these two values of x equals negative 3 and x equals negative 2, you get 25 and 16 respectively. Just put crosses here because it's an indication that it's a bit too high. I'll go ahead and fill out the rest of these numbers. So I've filled these numbers in and I've jotted the x values and the y values accordingly, and you can see here that it mirrors the y equals x squared graph, but it's being shifted 2 spots to the right. So that 2 spots to the right and the fact that this is a negative 2 kind of has an indication that whatever this number is, you get the inverse of it and then you shift it to that spot however many units. So in this case, considering that it's in brackets, so if it's in brackets, take the inverse and then shift it that amount of units. So if this was x is x minus 3 all squared, then we expect the normal y equals x squared parabola but shifted 3 units to the right. If it was a plus, then whatever the graph is will be shifted to the left. Again, we'll look at the x squared minus 3 and see what happens with this. Alright, I've gone ahead and filled in the corresponding x values numbers with a y output, and I've keyed that into the graph. And here you can see that again it copies the y equals x squared graph, but it's being shifted down by 3 units, and this is because of the -3 here. So if this was a x squared minus 12, this will be shifted 12 units down, and it would just be a copy of the y equals x squared. If it was x squared plus 6, then it'll be shifted 6 units up. So it's kind of the same properties as this. This deals with left and right. We're just going to be careful of the sign. It does an inversion of it. But when it comes to shifting up and down, it's whatever the sign is, it goes that direction vertically, and then however many units. So we'll be looking into just the different properties that we can get from all the different y equals x squared graph, and then just modifying it. We know what modifications will happen if there's a negative in front, if there's a minus or plus within the bracket squared, or if it's on the outside of the bracket. We're also going to be looking into dilation as well. What happens if there's a coefficient in front of the x squared? What happens if we add a plus x, or a takeaway 3x plus 2 if there's a constant? We'll be looking into all those different properties. So as I was saying before, the basic parabola has the rule of y equals x squared, and every type of parabola that is made is using this as a basis. But to look into the y equals x squared parabola, there's a thing called a vertex, and this is also known as a turning point. So where the part of the parabola gets to a stop and then goes the other way, so it's almost like the mirror line. The turning point for this ends up being at 0, 0. So it goes down, it stops, and then it goes back up again. This right here is considered your turning point, 0, 0. There are ways to find what the turning point is. For a basic y equals x squared, it's 0, 0. This turning point is considered a minimum turning point because it's at the minimum point of where it turns. If you had a parabola that looks like this, this turning point of 0, 0 will be considered its maximum turning point. This is if it's y equals negative x squared. So you can either have a minimum or a maximum turning point. It just really depends on whether there's a positive or negative sign in front of the x squared. So with the turning point in mind, the axis of symmetry is at x is equal to 0. The axis of symmetry is always at an x is equal to whatever value, and it depends on whether the graph gets shifted left or right. In this case, because it's right dead center in the middle, if I were to draw this dotted line here, that's to occur at x is equal to 0. So our axis of symmetry, where it mirrors, is at x is equal to 0. And then you have your y and your x-intercepts. They're both the same, and this ends up being at both the point 0, 0. The x and the y-intercept in this case is exactly the same. Now, a simple transformation of this graph is what I was saying before, dilation. So if you put a coefficient in front of the x squared, this will either squeeze the graph or stretch it out, depending on what number it is. If the number is higher than 1, the graph gets narrower because you're excelling at a faster rate. So it's going up much quicker than your normal y is equal to x squared. But if it's a number lower than 1, but greater than 0, so it's a fraction of some sort and it's not negative, this stretches out a bit more. It gets not squished out, it gets stretched out, fatter, as what they said when I was in year 11. And this is because the rate in which it's going up by is a bit slower because of the fact that you're applying a fraction, or you're multiplying it by a fraction, and depending on what type of fraction this is. So if you had something that was y is equal to 1 over 8 x squared, this will be quite a much fatter parabola that scoops around like that. We also have the two other types of transformations. You can have a reflection, and that's if you put a negative in front of the x squared. Again, you can also apply another number that's 1, but provided that it's negative, it will also have a reflection. So you can have a y equals x squared reflected if a negative is popped to the front of it, and then you can either squish it or stretch it out, depending on what the number is. And there's also translation. So you can translate the y equals x squared graph, either shifting it left or right, or shifting it up and down, depending on what number is within a bracket, doing the inverse of that, more importantly, and if it's going to be shifted up or down a certain amount of units. We'll look into two different examples of this, and then you can go ahead and tackle the set questions. Example one is we're going to identify key features of the parabolas. We're going to determine the following key features of these two parabolas here from the graphs. We're going to find that the turning point, whether it's a maximum or minimum. We're going to find the axis of symmetry and both the x and y intercepts. So let's look at A. So the first one here, the turning point and whether it's a maximum or minimum, this dips at its lowest point. So it is a minimum. So a minimum turning point. I usually write TP for turning point as shorthand notation. Minimum turning point at, and this turning point, because the point has been given to us, we just simply write what those points are. It's at 1, -4. And remember that this is Rx and this is Ry. Now graphs, especially at the start, because it's 7a, they will give you the turning point. There will be at times you have to find out what this turning point is if it hasn't been specifically given to you. But in this case, because it has, it's quite a simple one. You just say it's 0.1 -4. The axis of symmetry is the x value that it takes at that turning point. So the x value at that turning point is 1. That just means that at x equals 1 is your axis of symmetry. So you would just simply write x is equal to 1. That's where the parabola mirrors the left and the right at x is equal to 1. The x-intercepts are, there are 2 points of the x-intercepts. So x-intercepts happen when y is equal to 0. Right? And we're going to have 2 points. Sometimes we might have 1, sometimes we might have 0. Generally we have 2. It really depends on what type of transformation we make on the basic parabola. So the x-intercepts will happen when y is equal to 0. So we know both of these points here will be 0. The first one happens here when x is equal to -1. And the second one happens here when x is equal to 3. So these are 2 points. And this goes back to the previous topic that we were looking into, quadratics. You know how to find these points when you're given a graph. You just make whatever the graph is equal to 0, and then you use your null factor law. That's how we get these points, and that's the whole reason why we do the null factor law. But you'll see that later down the track. The y-intercept happens at this point here, where the graph cuts the y axis, and this happens when x is equal to 0. So our y-intercept is at -3. For the second graph, the turning point, whether it's a minimum or maximum, the turning point is a maximum, and because it reaches its highest point, so obviously we're dealing with an inverted graph, or there's a negative in front of the x squared. So there's a maximum turning point at, and this turning point is at -2, 0. So x value is -2, and our y value in this case is 0. The axis of symmetry is this line here, and it's always an x value of whatever the turning point is. So this is at x is equal to -2. We have our x-intercepts. So the x-intercept is where it cuts through or touches the x-axis. In this case here, it only happens in one spot, which is right here. So this will happen when y is equal to 0. It will be at -2, which happens to be also the turning point, the maximum turning point. Just touches it, and this is where we can only sometimes, not only sometimes, this is the situation where we have one x value or x-intercept that we look for within a quadratic. And the y-intercept, this happens at this point here. So when x is equal to 0, y is equal to -4. The next and last example we're going to be looking at is copying and completing the table for the following graphs. So we've got 3 different graphs, and they all have some type of transformation shift, dilation of some sort. No dilation. Yeah, dilation. And we're going to be looking at, do any of these properties happen, yes or no? And we're going to look for a maximum minimum turning point, what the y value is when x is equal to 1, and is it wider or narrower than y equals x squared. I'll go ahead and fill out the first one and explain why. So the first one, we're comparing the y equals 4x squared to the normal y equals x squared. This, just like the y equals x squared, has a minimum. The minimum turning point is there. It's not reflected in the x-axis at any point. It's just the same. So you would just say no. The turning point, just like the x squared, is at 0, 0. The y value when x is equal to 1 is 4. So when you substitute x equal to 1 into this formula here, you get x squared, 1 squared, which is 1. 4 times 1 gives me 4. And you can see here, when x is equal to 1, y is equal to 4, which is this point here. And is it wider or narrower than the y equals x squared graph? This is narrower. It's skinnier. Because this number is greater than 1, we're expecting the rate of this to shoot up faster. So it will be skinnier or squishier than the y equals x squared. The second one, we're comparing the x plus 2 all in brackets squared. So this is a shift to the left. So the inverse of plus is minus, so it's going to the left, and this is going by 2 units. Again, we have a minimum, because it's right here at the lowest point, dips down to a minimum. It's not reflected in the x-axis. The turning point is at -2, 0, because it's been shifted to the left twice. When the y value when the x value, is equal to 1, the corresponding y value is 9. So this is saying that when x is equal to 1 here, y is equal to 9, which is somewhere right here. So that's where the graph keeps going up and up and up. And is it wider or narrower? Well, it's neither. It's just the same as the y equals x squared, because there's no number that is in front of the x. Even when you expand this out, there's no number or coefficient of the x, namely the x squared, because of that, there's no dilation, there's no narrow, it doesn't become narrow, it doesn't become wider. That's what I'm trying to say. Okay, the last one, we have minus x squared plus 3. This right here is a maximum. Because of the fact that there's a negative in front of the x squared, this will become a maximum turning point. It is reflected in the x-axis. Because of the shift, it makes no difference. As soon as you see a negative pop in front of the x squared, there is a reflection. Okay, it's reflected to the y equals x squared. It's just being shifted up by 3 units, but that makes no difference. The turning point is at 0, 3, which is this point here. The y value when x is equal to 1 will be 2. So when x is equal to 1, y is equal to 2. And that's just by simply substituting 1 into this formula. And again, it's the same as the y equals x squared. There's no wideness, or it doesn't become narrower because of it. And that's because the coefficient in front of the x, despite it being negative, there's no dilation. There's no number or digit that's different to -1 or +1. That's it. That's all there is to this. I know this was a lengthy video, but there was a lot to digest for this. Remember, check your log sheet, because I've given you a modified log sheet of which questions you need to tackle. It's highly recommended that you also have graph paper. If you don't have graph paper, you can also always type in graph paper into Google Images, and if you have a printer, you can print that out. Usually I'll just distribute graph paper within class. If you don't have graph paper, then just make sure that you rule up your graphs when you go to copy them or draw them or sketch them. Best of luck, guys, and see you guys in the next video. Bye bye.